Okay, so recall that we are on example 10.1 and we are at part C. So part C is a little bit more challenging, but it will be more fun. So part C says we're going to rapidly cool to 650 degrees Celsius, hold for 20 seconds, then rapidly cool to 400 degrees Celsius and hold for 1000 seconds. And then we're going to quench to room temperature. So let's follow this on the IT diagram. So I'm rapidly cooling from above the eutectoid temperature and I'm going to 650. So I should be about somewhere here, and then I hold for 20 seconds and I end up about here. Let's check on the x-axis what's going on. So remember, this is a log to the base 10 type scale, because notice I have 10 here, then I have 100, then 1000, and so on. So 20 is actually about right there. And then 30, the distances between 20 and 30, 30 and 40, 40 and 50, and so on get less and less. And then we get to 100. So 20 is about here. So if I go all the way back up, my 20 seconds takes me on that 50% transformation line. Okay. So I'm here. Now I'm at 50% austenite, 50% perlite. I'm going to come down, all the way down. I'm rapidly cooling to 400. So 400 takes me in the ballpark here, right, in this ballpark. So I'm about here. When I am here, what's going to happen? Well, if you recall how perlite and bainite are formed, either of them are formed from austenite, but they cannot be formed from each other. There's a slide earlier back that indicates also on the slide that perlite cannot transform to bainite. Neither can bainite transform to perlite. Okay, perlite is only obtained from austenite, as well as bainite is only obtained from austenite. So let's come back down. We're at 50% austenite, 50% perlite. As we come down to this point tells us that we'll be at 50% austenite, 50% bainite. But the perlite that was up here will not transform. So we're only left with the 50% austenite that we had from here. So with that 50% austenite, when that transforms, it will transform to 25% austenite and 25% bainite, 50-50. So at this point, we end up with 25% austenite, 25% bainite, and 50% perlite. Now I hold for 1000 seconds. So I hold for 1000 seconds. From here, I'm at 20 seconds now. So 1000 seconds would take me all the way out. And then I'd go a little bit past this one here to 1020. But what is 20 on this scale? Look at this scale. This is 10 cubed. This is 10 to the 4th. So 20 is really tiny. So it really doesn't matter whether I stop here or I just go a little bit beyond. And also, another thing that we can do, or another technique that we can apply is, well, instead of starting here, since 20 doesn't really compare to 1000, we'll just go back to the beginning and go all the way out to 1000. Okay, so we can do that. And recall that we have 25% austenite, 25% bainite, and 50% perlite. But now I do the full transformation. I come across here. So whatever austenite I had, that will transform fully to bainite. So at this point, all that 25% austenite will have become bainite. So I'll have 50% bainite and 50% perlite. Now I rapidly quench. I come down below the martensitic transformation regime. But guess what? The only phase that transforms to martensite is austenite. So the perlite and bainite cannot transform to martensite. So I end up with 50% perlite, 50% bainite. Okay. And this these items in red sort of discuss this motion here where we moved all the way back to 1 or 0, almost 0, and then we went out to the 1,000. The same points, it makes the same points I stated previously. You know, the 1,020 doesn't make much difference at all, and the 20 is not really is much smaller compared to 1,000. Okay. Okay, some key points. Note that the diffusion rate is proportional to the temperature, as you would expect. You know, the higher the temperature, the higher the diffusion rate, and the lower the temperature, the lower the diffusion rate. Also, recall, we've said this a few times, that the diffusion rate is responsible for the formation of the lamella. So, if you have a high diffusion rate, then you'll have thicker lamella. Low diffusion rate, you'll have thinner lamella. Correct? Diffusion rate is not the same as transformation rate. The transformation rate is the rate at which one phase transforms to the other. That transformation can be governed by nucleation and grain growth, or not can be, it is governed by nucleation and grain growth. Sometimes one phenomena is stronger than the other, or is more dominant than the other. So we have to be careful when we're discussing transformation rate, and be aware of which phenomena is more dominant, whether it's nucleation or grain growth. And recall we said that grain growth was diffusion driven. Okay, so this table just summarizes the various phases that we've already discussed. I'll leave you, I won't go through this because this is just a matter of reading and recalling. Right? These are definitions. And when you practice the problems and you practice the IT diagrams, you'll find you probably don't have to sit here and try to memorize what's bainite and what's spheroidite and so on. Okay, a few examples. We'll go through a few more examples. Alright, so steel is rapidly quenched from above 727 to 650, held at that temperature for 12 seconds, then quenched to room temperature. So we're at 727 or slightly above it. We go down to 650, which is about here, and we hold it for 12 seconds. Holding for 12 seconds is going to take us to about this point. Alright, let's check out down here. Let's look at the x-axis for a minute. There is 10, there is 10 squared. So 20, this is 20 here. So 12 is about where this red line is. Okay, so we hold for 12 seconds, and then we quench to room temperature. So I'm coming all the way down to room temperature. So what's going to happen? Here I'm at what? 50% austenite, 50% pearlite. I come down. Well, remember, you come down here, you rapidly quench, your austenite becomes martensite. So I'll be at 50% martensite and then 50% pearlite. So in example B, we have steel that is rapidly quenched from 727 degrees Celsius to 600 degrees Celsius. We hold that for 3 seconds, quench to 350 degrees Celsius, hold that for 1,000 seconds, and then quench to room temperature. So let's go through that. From slightly above the 727 degrees Celsius eutectoid temperature, we go down to 600. We hold for 3 seconds. Well, 3 seconds is about here on the x-axis, right? So that takes us to 50% austenite, 50% pearlite. Then we come down, we're going to quench again to 350 degrees, and we hold that all the way to 1,000 seconds. So that takes us to about here, right? 1,000 seconds. So recall I had 50% austenite, 50% pearlite. Well, now all that austenite will have transformed into bainite. So here at this point I'm left with 50% bainite, 50% pearlite. then I quench down some more all the way to room temperature, and I will not have a change, because the only way I can get martensite is if I am going directly from austenite. I do a rapid cooling all the way down. That's what this regime is for. But otherwise, the pearlite, neither the pearlite nor the bainite will transform to martensite. So there we go, 50-50. The other examples I will skip, and I will encourage you to go through these on your own. That will be C, D, and E. Now let's look at the mechanical behavior of each of the iron-carbon alloys. Right? So cementite is much harder and more brittle, but more brittle than ferrite. And you'd expect that. Why? Well, to go from ferrite to cementite, we are increasing the percent carbon. Fine pearlite is harder and stronger than coarse pearlite. And this also makes sense, because if you think about our arguments we used when we were comparing fine-grained material to coarse-grained material. With fine-grained material, we had more resistance to dislocation growth or dislocation movement. So you end up with a harder, stronger material. Spheroidite is extremely ductile and tough. Well, you expect more ductility in spheroidite because this is a reheating process. You're heating up tempered martensite, you're heating up bainite or pearlite to just below the eutectoid temperature. Also, with the spheres, the sphere-like cementite globules that are embedded in the ferrite matrix, you get less phase boundary area per unit volume, which allows for more dislocation movement, or easier dislocation movement, as opposed to, remember, bainite, you had these needle-like structures of cementite embedded in the ferrite matrix. But with spheroidite, as it sounds, these needle-like structures become more sphere-like. Bainite is harder and stronger than pearlite. You'd also expect that, because bainite is formed at a lower temperature. And martensite is the hardest and strongest and most brittle for the same reason. It is formed at the lowest temperature of around 200 degrees. So here we see that yield strength and hardness and the tensile strength all increase as your weight percent of carbon increases, and that is due to solid solution strengthening as we would expect. And of course, the reverse occurs in terms of ductility, where you have a decrease in ductility as well as impact energy as you increase your weight percent carbon. And you can look back, and we discussed this in earlier chapters as well. Here we have the same thing happening. Just note for fine pearlite and coarse pearlite versus spheroidite, just note that the fine pearlite has a higher hardness than the coarse, because think of or the argument regarding grain size reduction and how that increases your hardness. And spheroidite also, because of the sphere-like shapes of the cementite that is embedded in the matrix, you can expect your dislocations to be less restricted. And also with ductility, it would be the reverse for those three bodies. Finally, we look at transformation temperature versus Brinell hardness. As transformation temperature increases, your hardness actually decreases when you're looking at the formation of bainite or pearlite. For bainite, you have to recall that the transformation is primarily diffusion driven, or for pearlite, it's primarily driven by nucleation. And if you think about how those phenomena occur with increasing temperature, in both cases you're going to have an increase in grain size or reduction in grain boundary area. This results in less restricted dislocation motion, giving you a softer material.